will move to the next presentation, and it will be Philippe Say and Matthew Rock, who is going to present us the EDUCAT Open Modular Adaptive Framework, and the OAS.
Good afternoon. Can you hear us?
Yes.
Thank you. Good afternoon from Ghent, Belgium, on behalf of VOCA, who is with us in the lab here, and our own team. So we'd like to present to you two parts of the EDUCAT project, the Open Modular and Adaptive Framework for Clinical Trials, and also the Obstacle Alerting System application. This is the outline, a short introduction. Then we will discuss the components of the EDUCAT framework very briefly. We move over to the obstacle alerting system, and we discuss some of the results and the measurement data in the direct analysis. Okay, let's start with the problem description. What we need, you may recognize the start of this slide. We develop technology in the project. We do clinical trials. We analyze the data, and the outcomes and the results are then used and also transferred to the society. So to do that, we need a lot of things. We need different sensors. We need different types of powered wheelchairs. We mix that with different test setups with different goals of the tests. We also have input from different questionnaires from daily diaries. We are having different persons in clinical trials. We do multiple tests, and we need a flexible analysis. So all of that together means, in fact, that we do need that open modular and adaptive framework, and preferably it should be in one single database combining all the heterogeneous data. The solution is, in fact, in one workflow. If you allow us some explanation, we already connected it to the powered wheelchair, but in fact it is open, and these three parts can be connected to any system. We have three main parts: the data management unit, an Android tablet that is mounted, in our case, on the powered wheelchair, and then we have in the cloud a database and web services. What is the workflow? First of all, you install for a trial or just for a new user, you install the sensors, actuators, the software modules. On the wheelchair, you see here, for example, distance nodes being mounted. You also see the tablet being mounted, etc. Once they are physically installed, you configure the setup. You set up the experiment by swiping in an app. So you see here, for example, distance sensors being added. You configure them. You do that one time upon start, and normally you reuse an existing setup. Then you run the measurement. You start the measurement, and data is continuously being sensed, stored, and pushed to the cloud. You have a live view, as you can see here on the tablet. You can fill in daily diaries. You can fill them in on another Android device, or the caretaker can fill it in for you. You can use the obstacle alerting system as a software instrument, if you like. In the end, you need to analyze all the heterogeneous data, which is in one single database. And as usual, we always have the help of Albert Einstein to do this. We also put ourselves some additional requirements for the framework. First of all, given the GDPR rules, we need to pseudonymize the persons involved. I finished a difficult word. We need to have a little bit of security built in, authentication upon login. We need to have a secure and a robust communication to the cloud, which means, for example, that we need to allow for roaming between Wi-Fi access point and also buffering when we are in an elevator or something like that. Finally, we need a very flexible graphic configuration, and to go quick during trials, we need a detailed first analysis, which is fast, and afterwards, if you want, in big amounts of data you can still analyze from the database. If we put all this together, we get a very powerful, flexible system for clinical trials, and the workflow includes indeed pseudonymization. Let's start with the last part, and it's finished. This is in fact the workflow for the clinical trials. And you will see when we enter a person in a clinical trial, we do one small part on paper. It's less than 1 page, which is in fact a paper acceptance. That holds the name of the person, of the end user, of the carer, etc. His address, his passport number, his contact details, in fact, and we assign him, in this case, a patient ID. This is typically done and also kept on paper by a physician, by a medical doctor. And that's the only place on paper outside of the system where the name of the person is kept. From there on, everything is first of all electronic. Everything is in the app, in the Android app, and in the database. It's all electronic, and the only thing we are using is that pseudonymized, something like that, patient ID. Point 2, the components of the EDUCAT framework. We have 3 main parts, as you saw: the data management unit, the Android app, and then we have the connection to and the cloud database itself. Let's take a look. Let's start with the data management unit. That one is in fact within the circle here. Don't worry, I'm not going to discuss this. This is just for the engineers so that they are happy. I just want to point out that the microcontroller is in a very small box mounted on top. I'll show you in a minute, but the idea is to show you that it's open. We are storing, we have a kind of backup on the SD card. Normally we are streaming the data via the Android link via USB to the tablet on the powered wheelchair. We have an inertial measurement unit mounted inside, also GPS tracking. This is the connection with the external commercial powered wheelchair. And here we are adding our own sensors. I'm showing this also because this allows, there is still free space, this allows other instruments from other vendors, from interested companies to be added to the system. So it's quite open. And you can see, you almost don't see it. It is right here. That is the DMU mounted during a test in Junia, in this case, under the wheelchair. The software is organized around 4 threads, which I'm not going to discuss, but you can read it later on. What is the basic idea? A configuration for the test, which we spoke about before, we mentioned before, and we'll discuss it later. Configuration comes from the cloud database to the Android tablet. The tablet is sending it to the data management unit, and the data management unit is in fact checking, is all the hardware, are all the sensors there, and are they functioning? And if the answer is yes, then it's ready for work. The whole system is ready for work. All the connections are made. One part of the work might be we stream data to the tablet. Let's take a look at that as a next step. So we move to the EDUCAT Android app, which is in fact placed in 3 locations. In this scheme, it's first of all normally fixed on the powered wheelchair. Most of the time it's used as human-machine interface for the visual interface with the user. If the user does not want to see it, we mount it underneath. It's out of sight then. You also see the Android app when we add a software instrument like the obstacle alerting system. And finally, you can use this or another Android tablet or phone to fill in questionnaires, and everybody could do that, multiple things at the same time. What are the main tasks of the Android device? Well, you see here, in fact, when you log in as a developer, you get to see a little bit more than the normal user. But what are the main tasks? You fill in and you view also questionnaires, including the daily diary. An interesting item to mention here is maybe that the questionnaires are not programmed in a hard way. They are in fact dynamically built using the data in the web server. So it means that we can easily add and adapt questionnaires. We do not need to change the app itself for that. It's also used to create new measurement setups. It takes care of the data stream with the DMU, together with the DMU, of course, and it also takes care of the TCP data stream to the cloud database. We can have a, I'm sorry, I skipped the measurement setup. So you can see here some sensors being added. You can configure them. I'll let you read that later afterwards. And live visualization was the next point. This is an example of live visualization. We'll show you one live in a second. I think live in a second is now. So a small demo with data streaming on tablet. We did not do anything else yet, just show that. Mathieu is switching.
So I first will explain what is on the left here. So it's a live view of it's a development system of the DMU, and here in the big wooden board is an equivalent of a powered wheelchair. So we have the joystick here, and here is the unit with the motor emulation. Here in the front we have the DMU, with next to it the TPI board. This one connects the DMU to the wheelchair. The little box on the right here is the IMU, and here is the GPS antenna. And if you look closely, you can see here 1, 2, 3 distance sensors, and the tablet is here, and the image of the tablet is streamed on the right side. So I will continue now. So in the app, you have a lot of different options, and the option I will show now are the graphs. So we have now a graph at the bottom, the accelerometer of the IMU. So you can see it on the left, I'm moving the IMU, and on the right, you can see the data from the IMU coming. So if I move it, you can see it live on the graph. And then at the top, we have the joystick deflection, and it's one line is for the speed, so it's forward and backwards. And then we have another graph for left and right. And of course, you can also do both at the same time. And the graphs are fully configurable, so you can add or remove instruments as you like. Okay, then I give the word back to Philippe.
Thank you, Mathieu. Let's go back to connecting all of this to the cloud database. Until now, we stayed here in the system. So let's now move to the connection with the database and the database itself. There are, in fact, if I go back, there are 2 data streams. So we are, in fact, transferring data from the data management unit to the Android device. This is a cable. This is quite reliable. From the Android device to the database in the cloud, it's either Wi-Fi or 4G. That might be the most delicate channel to use. So the first data stream between DMU and Android device is we send messages every 20 milliseconds. That is the rhythm of the standard rhythm of the measurements, and every message is acknowledged. There is also an acyclic data stream in between, for the commands and responses between DMU and Android device. And we use a cycle counter to detect each message and to check for missing ones. Between Android device and cloud database, we keep the same rhythm. We also have the acyclic messages, and well, as you already saw, it's Wi-Fi or 4G. We designed for robustness. You have here the sensors, CAN, the DMU Android device database again. There is a small buffer in the DMU. If a message is missing here, the Android device immediately asks back where it is, and the answer comes back. This is very short time. This is the most delicate channel, so we implemented in the Android device a 5-minute circular buffer of all the messages. And if the database sees that a cycle counter is missing, he asks again to the Android device and he picks it from his circular buffer. This allows us to transfer all the messages, and it also it's buffering if we have problems with the connection, or if we are roaming. We might be roaming from one Wi-Fi access point to another one, or between Wi-Fi and 4G and back. And well, the 5 minutes is more than enough to buffer that. We do not acknowledge the messages here. It's to begin with the TCP connection, but every block of 1500 messages arrived completely in the database is still acknowledged. That is still something that we do. So it's quite robust for security. I already mentioned that we have authentication with the HTTP digest access authentication. You can read a little bit in between. So you log in with the user ID and a password. It's anonymous. And there is TLS encryption of the data. The data itself, the database itself, holds all the information, and it's quite heterogeneous. It's measurements, it's questionnaires and answers, it's measurement setups, etc. We have different kinds of access. There is, of course, direct access for the programmers. There is a read-only access for data analysts if they want to do queries. We experienced already a long time ago that when doing clinical trials, we want to see quickly a first analysis of the results. So we designed quite early in the process, and we kept on improving the MATLAB live script so that we can make very quickly reports. And there is also another access via the website, just to give an idea of how the website, the database, excuse me, is conceived. This is, for example, how the questionnaires are all inside the database, and this is more in detail. I'm sure you will all have a look at that when you take a look at the PowerPoint later when it's on the website of the project. I'm not going to discuss this now, but what might be important is the website access. That is for our questionnaire management, making questionnaires, also for the user management. I'm not going to discuss this in detail, but making the questionnaires, making a new questionnaire is on a website. It's not, and all the answers and the concept goes into the database. It does not go directly to the Android app, of course. And for example, for managing the different user types that we have a system for researchers, vendors, and all kind of other types of users that we have here. It gives you an idea. I think we go to see how a questionnaire is filled in and how we can view a submitted questionnaire. I think Mathieu will do that again.
So like Philip already mentioned, we are going to fill in a questionnaire as an example. So here you have a list of all the available questionnaires. If we open a questionnaire, some of the users have more permissions than other ones. So for example, I have the permission to fill in a questionnaire for myself, but maybe a carer or a researcher can fill in questionnaires for other users, of course. So, and the first screen we have is an intro. So here you can have some information about the questionnaire. And then we can go to the next question. For example, here is a question with only one answer possible. We also have questions with multiple answers or fill in fields to fill in. So yeah, you can just pick an answer and go to the next question. And then I will go a little bit faster to the end of the questionnaire. So here, and then at the end of the questionnaire, you can have an overview of all your answers. And if you want, you can go back and change something before submitting the questionnaire. So now it's going to be submitted. So that's okay. And then once it's submitted, we can also use the app to see the answers of the questionnaire. So here I load in the questionnaire that I just submitted. And then we can go over all the answers. It's similar to the overview while filling in the questionnaire. And then at the top right corner, you also have a button, and that's the option to save the answers of the submission as a PDF file on your Android device. Okay, and then I will give the word back to Philippe.
Thank you very much. That's filling in a questionnaire. So now let's take a look at the obstacle alerting system. with two main parts. In fact, we needed to add to a standard commercial wheelchair distance sensors, and then we needed to design and add a software instrument to obstacle alerting system itself. It's to be considered the driving aid for powered wheelchair users. It's very similar to a parking system in a car. You have here the view on the obstacle alerting system. It's not a car, of course, but it's a powered wheelchair in our case. So we add distance sensors. We need to measure the distance in every direction. We need the software instrument that you are looking at here for calculations and feedback. The feedback can be a buzzer, can be haptic, and can be visual active here on the screen. And upon request of end users, and I think Yassine repeated it a few minutes ago, there is also a rear view camera. The rear view camera is in fact not in the framework itself, but it's still controlled by the DMU, so that every time that the powered wheelchair is moving back, you have a rear view image of the camera. You can see here how the tablet is mounted and how the obstacle alerting system here in a very early testing phase is present. Adding distance sensors for the obstacle alerting system, our French colleagues added ultrasound and infrared types, both of them, and they are connected via our own designed CAN bus system to the DMU. It's very flexible for mounting and connecting with the black-blue connectors here, and it was mounted, for example, during the Junia tests in 2021. They are mounted here, of course. You see the connectors, you see here the distance sensors, and I already showed you that the DMU is in fact there. And you can see if Ali, I think, is keeping his hand before the distance sensor, you can see that this distance sensor detects something very close. The software instrument itself, the obstacle alerting system, it can work on its own. It doesn't need a cloud connection, of course, but if you use it in a clinical trial, then we are continuously streaming data as a software instrument, just like all the other instruments. The obstacle alerting system itself provides a lot of data. It's continuously detecting which of the feedbacks is active, which of the sensors you enable or disable, because you can, by simply clicking on them, you can enable or disable them. We measure, of course, the sensor distance. We keep the OS result. There is danger or no danger, etc. The OS characteristics, all are there. Speaking about the OS characteristic, this is an example here. The alarm distance is function of the speed of the wheelchair. You can, of course, configure this, and you can even test it. This is how it looks like in the app itself. I think we will now see, I hope that we will now see two movies, one configuration of a setup, including the OS system, and then the second one you will hear in a minute.
So like Philip already mentioned, I'm going to show you how to create a setup. So I'm going to create a new setup especially for today, for the closing conference. So we can create a new setup. It's also possible to create a setup from an existing one, but now we are going to make one from scratch. So we fill in the required information, and now we click create. And then we get to this screen, and here on the left you have the view of the wheelchair. And then here will be the instruments that don't need to be placed on the wheelchair, and here will be the instruments that need a place around the wheelchair. So first, going to add a joystick. It's one from Dynamic Control DX2. So like this. And then also a joystick profile. And like that. Okay, now we go a little bit fast forward, and then I've added all these sensors. I will explain them in a moment. And then you can also see there is already a distance sensor here, and then I'm going to drag the other two sensors to the setup. So like that. And then this is the completed setup. So yeah, like mentioned before, we have the distance sensor here at the front of the wheelchair. We have a joystick with 5 joystick profiles. Then we have the IMU, the GPS, the real-time clock, the Android device itself, and the OAS system. And then if we have a setup, we can, of course, do some testing. And for a first test video, we have a test from my colleague Arne in the wheelchair in the hallway next to our lab in Ghent. So you can see him. I hope you can hear the sound. I think so. Yeah. And now we have a split view of the tablet, and so you can see in real time what the sensors are detecting. You will also see is going to take a left in the next hallway, and you will see it perfectly at the front sensors, like that. Okay, and then we move to a small video from our colleagues in Lille from Junia, and they have built a little parkour with obstacles. And they also use special goggles to simulate disability. Okay, and then I will give the word back to Philippe.
Thank you. I hope they had the sound off in Junia while doing those tests, because I think it was quite a lot of noise. So if we have all the data in the database, we may consider doing a quick analysis. So you could do this while doing a full day of measurements, one parkour after another. We could do all of this. First of all, the setups, the measurement list, basic properties of the setups, they are all available in the app. So usually when we take a look at measurements, we have an Android tablet or phone next to us, and we have our PC. And normally we take a look via MATLAB live script for the analysis of the data. So let's take a look. What can we analyze, or what are the options? Let's start with that. Some options: we can select a measurement. We are now close to 1,000 measurements in the database. We are at 990 or something. We will take a look later on. You can select a full measurement or a part of it, make some parameter choices. Then you automatically generate a full range of plots and calculated values. And the report can be stored in HTML, Word or PDF format. And in fact, you only need to get the measurements from the database one single time, because you can store it locally on your PC as a measurement object. It contains then exactly the same information as the information in the database, or you can even store the individual variables in the MATLAB workspace by storing the workspace itself. What do we calculate? We calculate, or we keep an eye on the operating times of the joystick. We calculate also the cumulative joystick path length. So it means, in fact, how much distance have you moved the joystick, and I didn't want to show it from the beginning because you would run away. We also calculate the normalized jerk score, which you can find here. Let's take a look at an example of an HTML result. It's a measurement done in Canterbury Hospital apparently on the 24th of May in 21. And you can see that it was probably Matthew driving around, and you can see an aerial view here. He never knew that we were watching. This is the path that he followed between in buildings and between buildings. So let's take a look at the HTML result of that test. Thank you. So we got the measurements, so we choose the measurements from the database. You can see that we are very close to 1,000. I wanted to check this. Yeah. So we took the 900 then, I think 84. I don't see it here. 86. Yeah. Okay. Yeah. The 86. We take it from the database one time. This is not so important that you see all of this. You can cut in time. This is the complete acquisition. It was in fact a parcours that he was following. So we want to analyze in fact from this point here until this point. So we are still going to cut in time to fit the beginning and end point. I don't know what I did, but it moved on. Yes. Sorry. So we will cut in time, start and stop times. We will do filtering also the dead zone of the joystick. And we will indeed calculate all of these things. We chose to do that. So in fact, then you just hit the plot button, and after a few seconds, you get all the plots. You can see that we have cut in the data, the beginning and the end are gone. This is the actual speed. This is the turn and speed of the joystick. He used profile number 6. This is the joystick deflection pattern. And then you get the heat maps, a standard 4x4 with the raw data, a 10x10 with the raw data, and then you get the same thing but with the filtered data. So you can see that around the center point we don't have a lot of measurement points. While I'm scrolling through this is generated in exactly the HTML report that we're looking at is generated in 6 seconds, so it doesn't really take a lot of time. This is turn and speed of the joystick in function of time. We take out the parts where it is not actuated. This is the filtered data, the same thing. This is the instantaneous joystick path length in each sample in the X and Y direction. And then we see here, in fact, what we wanted to calculate, the cumulative joystick path length, which is this one, and the smoothed normalized jerk score, they are here, and this is the cumulative one, and this endpoint is of course the 26,000 that you see here. This is more for us out of curiosity. This is the same calculation but on the filtered data. I'm going to skip this. You can see here the IMU data being displayed, all of that. The GPS is here. I think we are very close to the Greenwich meridian. We didn't have all the time reception, I have the impression. And this is in fact the path that Matthew has taken through the buildings, and this is how we see it with publicly available data. In the end, not until the end, you can see here the obstacle alerting system, the buzzer, the haptic feedback, and the visuals. Two of them were always on and the buzzer was off apparently. And here you see for each of the distance sensors what has been measured. More than 250 means that he didn't see anything in the range of 250 centimeters. So you see all the data here of the sensors, the distance sensors. In the end, you could see, I didn't mention this, but we can store the whole measurement with all information as an object in MATLAB format. We can even save the variables in workspace format. This means that if you do this, if you save it in the object format, that the next time you do not need to pull it from the database, but you have it locally on your PC. And in the end, you can save the live script as a report in PDF, in HTML, and Word. And we were looking at the HTML one in this case. I think we go back to, I don't know what. Yes, we still have the view here. Okay, how much resources does this take us for the ones that are curious? In the database itself, in the server, one stream, continuously streaming, measuring, is about 1.5% of the CPU load of one of the CPUs that we are hiring. If we are using the MATLAB live script on a PC, then you can see for a short measurement, it's a measurement of 2.5 minutes that we will show you. Part of it will be shown in a minute or two. If we have a short measurement, 2.5 minutes, that's around 7,500 cycles of 20 milliseconds. Processing takes us 2.4 seconds processing means splitting the data blobs from the database into the MATLAB variables. Plotting all the data, one heat map is 0.3 seconds. All plots take us 15 seconds, and generating the HTML report, 7 seconds. If you do the same thing with the measurements of 3 days and 3 hours in this case, you have, that's our measurement 906, you have more than 13 million cycles. It takes us 46 seconds to split the data blobs into MATLAB variables. A heat map still only takes 0.7 seconds, and making all the plots, and you saw that there are really a lot of plots in the report. Making all the plots takes us, in this case, it was more than 3 days of measurements, a little bit more than 6 minutes. Curiously, this is probably Windows being acting very strange, because generating the HTML report was shorter for this one than for that one. I think that the short measurements of 2.5 minutes is now going to be shown with a film, with a movie, excuse me, on outside this time on KU Leuven Ghent campus. And we also saw here what is happening. It was somewhere in the green area of the campus, and you will see Arne driving from here, crossing the road, turning, going off a curb. You will see it live, how the IMU is detecting it, and he's then returning back. So he will cross the street, go off the curb, you will see, and then it comes back. You will not hear a lot of sounds. The obstacle alerting system is active, but there's not much around him. You will see him crossing the street. We open a split window, and you will see that he takes a turn afterwards. And when he goes off the curb, you will see bikes passing and a car coming, but he survived. And there you see the IMU detecting a very heavy curb. Thank you. And then I think we arrived to the conclusions. So we realized within the project a powerful, open, modular and adaptive framework. It holds 3 main parts: DMU, Android App Cloud Database. We have a tool for a fast initial analysis, and the whole system generates and processes a lot of heterogeneous data. We also discussed in this contribution the obstacle alerting system, which is an adaptable software instrument with extra distance sensors that can be used standalone or as an instrument, one of the instruments in a clinical trial. Thank you for your attention and your patience. Are there any questions?
Thank you very much, Philippe and Mathieu, for that very detailed presentation, and it shows more in detail the powerful tool that we build up, so the framework, and how that framework can be used in an application. So in that case, it was the obstacle alerting system, and what was really very important for us, it was to collect all the data in the same database, and after have some analysis very quickly done. Because before, when we used the SD cards, it was really a huge job, taking weeks and weeks. So now it takes a few minutes. So we can really see the difference. So as we are a little bit behind our schedule, if you have questions to our to Philippe or to Mathieu, please